All right, let's get this to go. Okay, so you guys were doing this question as your do now question. I know I started with this question and then I've realized in hindsight that actually this was a really hard question. It was actually much better later when you guys have learned some stuff. And I can tell you guys are actually improving because I can see that you guys have answered this question far faster than the other questions that I've covered, which show, and this is a harder question, so it shows me you guys are picking up the stuff, which is good news. All right, so as we're working through this, some things to keep in mind is first thing you need to do is figure out what function group you have. You have this resource sheet here, and remember, I'm also going to let you guys take in, let me just grab my cheat sheet. I should call it cheat sheet. There you go. Your personal student resource sheet. So remember, for this internal, there is no requirements that say it has to be closed book. I don't want to do it fully open book because I'm worried you guys are going to get lost in the sea of notes and then not answer the question. So I want you guys to come in with one page, double-sided, with any notes you want for the internal, okay? I have printed off this because I think it's useful to kind of see all the function groups in the IR spectra, just because I find that this sheet here doesn't give you the shapes and things, it just gives you the regions. And so I feel it's useful to have both of them. So that's why I've done that. So first thing you need to do is figure out the IR spectra. Hopefully you've seen enough of them that you can kind of look at it right away and tell that that's an alcohol. If not, use this resource sheet to help double check it. Also, you have, like I said, this resource sheet as well. So I know this is an alcohol because I, like I said, use the CH as a compass guide to figure out where I am in my IR spectra, and then I look to see on the left and on the right, what do I see? When I look to the right, I'm looking at 1700, so that's 1500, here's 1700. And you notice when I'm looking at there that there's no peak, so that tells me no carbonyl. No carbonyl. All right, you guys need to know the vocabulary because I'm going to talk about function groups as if they're names. All right, so then I look to the left and I'm looking to see if there's anything between 3,000 and maybe about 36,000 to see if there's a peak, and I can see that one there. Now, what I need to figure out from that information then is it an amine or is it an alcohol? So again, when we look at the resource sheet, I can see that the alcohols are between 3,200 and 3,500, and the amines are between 33 and 3,500. So they're in the same area of my IR spectra. So I need to know what the two look like in comparison. So that's when I go to my personal resource sheet and I look. Miss has given us an alcohol. Miss has also given us an amine. I've ruled out amide because there's no carbonyl. All right. So the thing that we notice with the difference between these two is that with the amines, I tend to give you primary amines because they have the two little peaks, which I think is useful to tell. If I gave you a secondary, it would just be the one little peak, but it tends to be quite small and very kind of like, it looks like a camel hump in my opinion. Like it looks pretty distinctive, whereas this one looks like a real kind of big trough. Yeah? So when I look at this guy here, even though it's not as wide as this OH, it doesn't, to me, look like an NH. So I would then go that this here must be my OH because I have a peak at between, I want to say 33 and maybe 36. Are we okay with that so far? Cool. What else did I want to say? If at this point that I wasn't sure if I had an amine or an alcohol, what I could look at is at the mass spec. And remember, the integration of the spectra is going to get you up to the excellence level. So I am jumping to excellence real quick just to point it out. So remember, with the mass spec, the molecular ion, if a nitrogen was present, it would be an odd number. And we can see that it is an even number. So if I was on the fence about whether I was deciding if it's amine or alcohol, that is where I could double check it. So even number, therefore no nitrogen. Confirms not, or no amine, I should say. So we're getting to the excellence level in that bit, but that's okay. I'll go through and I'll do all the achieved first just so you guys can be reminded of what I need in order to pass. And then after that point, you guys can basically relax because you have 3 credits in the bag. All right. Next thing I'm looking for then is if you come to the CMMR spectra and you figure out how many carbon environments there are. This is just a matter of counting. 1, 2, 3. So 3 carbon environments. So remember, the achieved is just labeling the obvious. All right. And then last thing that I need for the achieved is just labeling things so that way I know you know how to read the mass spectra. So for this one here, recognizing that this here is the molecular ion. In this case, I have labeled it for you because it is way like I cut off the graph obviously, and then on top of that, it would have been a really, really small ion. So I've labeled it for you. If I haven't labeled it, it's one of 2 reasons. One is that it's obvious, and then you guys should be able to see it. Or 2, I've given you something like the empirical formula, so you know ratio-wise what your mass should be. So I always give you some hint in some way. All right, next thing then is my base peak. Remember, you're looking to see which one's at 100%, and that is my base peak. And if I was doing the math, that is 85, 86, 87. All right, and that is all I need for the achieved. Congratulations, you have 3 credits. Yay. Super easy. All right, let's now build this up to merit and excellence. Unfortunately, it is a really big jump from merit to excellence because you have to figure out what the molecule is. You need to figure out a potential molecule that fits these parameters. For the excellence, it is actually a reasonable step as well because now you need to start eliminating things and telling me what it's not. So this one is actually quite a fair differentiation between achieved merit and excellence, I would find. Whereas if you guys remember with redox, it wasn't a fair differentiation. If you were trying for merit, you might as well try for excellence kind of thing. I would still say do that because it's not that much extra in comparison to other like standards in like bio and physics where it's actually quite a big jump between merit and excellence. All right, so let's go through and work our way through and figure out how many carbons we need. So the first thing I do, so I'm now switching to orange because this, actually no, I'll put it into blue, because you would need to do this anyway for merit. So remember, I need to see the workings and I need to see your justification. If you just write down the molecule without any justifications, I can't give you the marks. So I know some of you guys did do that and you figured out the molecule, but I need to see the work behind how you got to that molecule as well. So first thing I would do is I would figure out what my alcohol would look like if it was on the N carbon and figure out the mass of that. So I'm starting with that molecule there. And when I do the math, I have 12. Let me just get my calculator. I have 12 plus 2 plus 16 plus 1. So the mass total for that one is 31. Oh no, someone's researching something and it's coming up in emails. Are we okay with how I got that? All right. Just be mindful that on the back piece of this paper, you have all the masses that you'll need. But on top of that, I've given you the mass of common fragments, and you'll see here at 31 that you do have that alcohol. So I do give you some shortcuts. All right, now comes the game of adding 14 until we're 1 away, because remember 14 is that CH2, and that's where I'm getting that 14 number from. So basically asking how many CH2s do I need to add until I'm at the end of my chain, and then I just add the 1 hydrogen at the end plus 1. So add 14, I'm at 45, add 14, this is going to be a while, 59, as you guys know, add 14, I'm at 73, add 14, I'm at 87, add 14, I'm at 101, add 14, and now I'm finally at 115. And then I plus 1, because it's my N hydrogen, now I'm at 116. Cool. All right, now I need to go through and count how many carbons I have there. So every time I add 14 is another carbon. So 1, 2, 3, 4, 5, 6, plus my original 7. So you have 7 carbons. All right. Now, to show, like I said, that integration of spectra for the excellence, I know that the mass has 7 carbon, but I only have 3 carbon environments. So if I want to get up to the excellence, I need to explain that integration between the two, and that is I must have symmetry in my molecule for this to occur. So we can do a little note there. So we found that mass tells that the molecule has 7 carbons, but CMMR only has 3 environments. Oops, running out of space. Therefore, we have symmetry. Because when a molecule is symmetrical, then I have the same carbon environment, so I'm double counting them. Don't know if Ms. Booker has any paper in here. Oh. It used to be right there. Oh, right here. Should I paper here? I'm gonna steal.
You want to refill?
Thank you. Good call. All right. So now let's start drawing out my molecule and figuring out what I have. So some of you guys might have drawn the 5 carbon molecule, sorry, the 7 carbon molecule as a straight chain. Now this is actually getting you up to excellence now because you're telling me what isomers it's not. So that's why I'm going back to the green. So 1, 2, 3, 4, 5, 6, 7. Let's say you put the OH here. And let's fill in the hydrogens, because we're good chemists. All right, so when I look at that molecule here, it's already, I know it's not the right answer, but it helps me kind of think about what's happening. I see that my alcohol's on carbon number 1, but with it being on carbon number 1, I've lost the symmetry, so there's supposed to be 7 environments. So from that, I already know that's the wrong answer. All right, so my next thought process when I'm going to this is, okay, I need to move the OH into the center because then that gives me some symmetry. And let's see how many carbon environments there are there. So if I go 1, 2, 3, 4, 5, 6, 7, and I go to the center carbon here, OH, like that, now I have some symmetry. But is it the right number yet? No. So when I do my counting, this is carbon number 1. These two have the same environment, so that's 2. These two have the same environment. There we go. There. That's 3. And then these two have the same environment. That's 4. So I currently have 4 carbon environments, not the number of 3. So that's now ruled out. We're getting closer. All right, so my next move then is, okay, I need to have some branches. So I'm going to be moving the N carbons to make some branches. Now, there's no point in me putting it on to these carbons here because then I still have the same molecule, right? So now I go on to the next carbon inward, and that can have a branch. And in fact, when I do that drawing, it's going to work out. So we're going to now have a 5 carbon chain. 1, 2, 3, 4, 5. That's going to go on carbon number 1. That's going there. That's going there. CH3, 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 CH2, CH2, CH. Let me just get some different colors so we can identify the carbon environments. All right. So all of these are methyl branches, and when I do the working, I can see that they all have 3 carbons, and then when I check to see what branch they have coming off of it, they all have the same branch. So this one, this one, this one, and this one, they all have 1 carbon environment. Then this one and this one have the 2nd carbon environment. And then this one in the center has the 3rd carbon environment. So now I finally have a molecule that has 3 carbon environments and meets all the other requirements. So this is one of the potential right answers. There were 2 right answers, and And let me show you the other one, which is basically taking these two guys and putting them onto the middle. So that way I had ethyl branches. So 1, 2, 3, 4, 5. That guy over here, this guy over here. 1, 2. There's no H there. That was my third option. Sorry, my next option. And then when I go to check carbon environments, these guys all have the same one. These all have the same one. And this one has the same one. Cool. So both of those are correct answers, and now we have to use the fragments to figure out which of the two are the correct answers. So let me tell you then some things for merit. If you had figured out either one of these two molecules, you got a merit. Now there's one more thing I need for the merit, and that is the fragments. And then with those fragments, you can use it to help you determine which of these two is the right answer. So when we're talking about fragments now, we are talking about how, if you guys remember when we were talking about the mass spec machine, the mass spec machine broke up the molecule because it wasn't stable as it's charged, and it broke up in different ways. And that's what resulted in this data set here. Now, this base peak here is really important because that tells us the most common fragment. Now, you don't have to necessarily identify that as being your answer, but it does tell you where it commonly breaks. Okay? You figure out the way it breaks the exact same way that you would figure out the mass of the ion, which is basically you're just adding up the carbons. So, for example, now I'm going to just try to get some different colors. Let's say I lost a methyl, like that, and that fell off my molecule. So if that fell off, that would have a mass of 15. Now I know the mass of my total ion as well. So if my total ion is 116, and I subtract away 15, what that tells me is the remainder of this ion is 101. So we're just thinking about how we slice and dice this molecule up, and then we're seeing how does it slice and dice on this guy here. Okay? It could also slice over here like that. And I could have this molecule here. Let's figure out the math. So that's 15 and 15. And then that is 14. So that tells me that I could have a fragment of 44. And then if I do the subtraction, 116 minus 44, that tells me you have a peak at 72. So these are things I can look for on the mass spectra to see, do I have those peaks present? So I'm just going to have a quick look. I'm looking to see, do I have a peak at 92? I'm looking to see if I have a peak at 44. So I have one at 45, but not quite at 44. I look to see if I have one at 15. I could also look to see if I have one at 101, that sort of thing. So that's my first molecule. Let's check my second molecule and see how that guy breaks up. So one of the ways that this guy breaks up that's quite different is it can lose CH2, CH3. So this is a unique fragment that you can't get from there. So if I do the math there and I have 14 plus 15, I have a mass of 29. Now there's no way for me to cut this to get 29. Actually, is there? There is, but it would have to have two cuts. It would have to cut here, and it would have to cut here. And then I would get a fragment of 29. You see? So 29 is possible. The other thing that I am thinking about is what is the total of this mass here. So if I do 116 and I minus 29, I get 87. Yes? Yes, we're cutting it to see what we see on the mass spectra. So this is the fragments that have formed from that main molecule, and I'm seeing what fragments are common. Now, depending on what fragments are common for each cut, it then tells me what I have molecular-wise. So when I looked at how this guy was going to cut, if it was going to cut, I would likely lose a methyl because there's so many methyl bits to it. So I should see a 15 and I should see a 101.
Now, which one after the two?
Basically, yes. Yeah. So, and then the other option is I can cut it here, because this should be a common cut. It tends to cut near the functional group because it's least stable there. So I would expect it to cut here, and when it cuts here on that side, it could also do the exact same thing where it cuts here, and I have that molecule instead. So it's a common fragment that I should see. I should see something at 44, I should see something at 72. When I look over though, right now, I don't see those numbers. So now I'm going, ooh, let's check this molecule here and see if I have those fragments commonly there. So with the way this one's going to break, the functional group's in the middle, and both of them have ethyl branches after it. So there's three ethyl branches that could break off. So it means that regardless of how I cut it in the molecule, I'm going to get the same fragment. So I should see a big fragment at 87, and I should see one at 29. What do I see there? 87. And then 29, you see another fragment, whereas in the other two, you didn't see those two. So from that information there, I can be confident to say it's the second one. All right? So fragmentation tells me more detail. So from that information, this is the right answer because of the fragments. Because I do see an 87 peak, and that's actually my base peak. All right. Now, in order to get your merit and excellence, I need to first see for the merit that you understand fragmentation. So you've identified one potential fragment. So for example, you can identify this fragment here, and you can tell me that that fragment is CH2CH3, which is 29. You can also tell me, like, you just have to do it once, but if you give me more answers, then there's more evidence. So in case you make a mistake somewhere, I can give it to you somewhere else. You don't have to identify the base peak. I just happen to have identified the base peak, and I know from that one, it's going to be that minus the ethyl. So 1, 2, 3, 4, 5, OH. Oops. No hydrogen there. Now, when we are identifying the fragment, make sure you have that little positive sign on there. Actually, it should be on the right to indicate that you know that that's the fragment. So, because remember, the positive sign is the charged particle, and that's going to show up on the mass spectra. So I'm just identifying potential fragments. You don't need more than one, but if you want to do more than one, it gives you more evidence. So that's what I need for the merit, is that you identify a fragment. Even if you got the fragment wrong, and let's say you use this molecule instead, remember there was a way to get 29, and if you just identified that, I could still give it to you. So you're just playing with that. For the excellence, I also need to see that you understand what was lost. So if this was the fragment that was being read on the mass spec, the other half of the fragment is not charged. So the other half is your CH2CH3, and you just show that with a dot to show it's the uncharged component. So that way, if you put these two things back together, you have the ion again. So that's what I'm looking for the excellence, is you understand putting it back together. All right. When you guys get stuck and trying to figure out the fragments, like I said, you can draw your molecule and cut it like that. The other thing that I find helpful is doing some subtraction and figuring out, okay, what is being lost in that. So when I did 116 and I subtract 87, what I find is the difference here is 29. And so I can use that number of 29 and go, ooh, let's go on the resource sheet. Does there anything that has a 29 on there that could hint to me what that 29 is? So there's lots of different ways mathematically you can figure out what's going on. So either you can, like I said, cut up the molecule like that, or you can just do subtractions and see what has been lost. Because you're looking for stuff like that are sets of 15, like 15 and 14. And that's basically all you need to do. And the last thing for integrating up the spectra is looking here and just confirming you have an OH. So if I looked at my carbon environments and I was looking for an OH that is not on the primary carbon, so not on the N carbon, it's between 50 and 90. And I see that there, between 50 and 90. So that confirms CO. That's it. So this is a very puzzle-like internal. There's not really a way to study it, like rote learn it. You kind of have to just keep doing practice problem after practice problem after practice problem. For you guys to be aware, my plan is to give you guys your first attempt on Friday this week. So tomorrow I'll give you guys a study session, and Friday I'll give you your first attempt. Remember, I'm going to give you 2 attempts like with redox, and I'm going to take the higher of the 2. So I'll give you first attempt on Friday. That gives me the weekend to mark it, and then I'll give you the feedback on Monday so you guys know what your grades are. If you are happy with your grade, then you're done. If you're not, you do a second attempt. Next week, we don't have a Friday lesson because of Mariki, so I'll see how well you guys do on the first attempt, and I'll make a decision on whether or not we do the second attempt on the Tuesday of next week or if we do it on the following Monday and give you guys the long weekend to study. So I'll see how you guys go. All right? Questions, concerns, comments? Nope? All right. So let me just pause the recording because we're done with that.